Usually the dynamics of a system can be obtained by considering the variational principle, but we can also do the reverse. So starting from dynamics, the famous equation F equals ma, we can derive the variational principle. In this case, for simplicity, we will consider just a system that consists of a particle, just one particle. So we have the mass of the particle times the acceleration, which we can rewrite as x double dot, the second derivative of the position of the particle. So we get the acceleration. This is equal to the force on the particle. So this force acts on the particle. Now, this force can also be rewritten, if we consider for simplicity a conservative system, as minus the derivative of the potential energy with respect to position, minus dv over dx. Now we can multiply both sides of this equation by delta x, so the variation of the position dx, or delta x, minus dv over dx delta x here as well. Now we can also multiply by the differential of time, and we can integrate along some path. We need to find the variational principle, and this is the right approach. So we multiply both sides of this equation here by delta t, so mx double dot delta x dt equal to minus dv over dx delta x dt, and we integrate over some path. Now let's move this to the right hand side, so we get integral of minus m x double dot delta x delta t minus dv over dx delta x dt equal to 0. And now we can integrate this first term here by parts. How? Well, let's do it below. I can rewrite that first part like this. Integral of minus m. The acceleration can be written as the derivative of the velocity, so dx dot dt delta x dt. If we integrate by parts, we get that this is equal to minus m x dot delta x, and we have to evaluate this at the endpoints of our integral. But remember that at the endpoints, when we want to consider the variational principle, this variation here, delta x, is equal to 0. So this will give us no contribution. Then we have plus integral of the mass x dot, and then we have the derivative of the variation of x dt, like this. But the derivative of the variation can also be written as the variation of the derivative, because these two operators are independent. We have delta x dot, and this term here, since the variation acts like a differential operator, we can also write this as delta mx dot squared over 2, which is the kinetic energy. So we have the variation of the kinetic energy, which I will call t. Therefore, this is just integral variation of t dt. This t here is the kinetic energy, whereas this is just time. So all in all, we can rewrite, if we insert this variation here, integral of variation of the kinetic energy minus, here we have dv over dx variation of x dt, but this second term here can be simply written as the variation of the potential energy. The potential energy only depends on the position. We are considering, for simplicity, just a conservative system. So this is equal to 0, and we can rewrite this as variation of the integral of kinetic energy minus potential energy dt equal to 0, and the kinetic energy minus the potential energy is simply defined to be the Lagrangian. So we can write this as the variation of an integral of the Lagrangian with respect to time equal to 0, and we have obtained exactly what we wanted. We wanted to obtain this variational principle starting from dynamics. This is just Newton's second law.